Hi, and welcome to my presentation, and thanks for the introduction. Actually, it was what I was going to say. So in this presentation, the content that I'm going to present, first I'm going to introduce the domain of the work and the problem that we are facing with industrial partner. And then I'm going to show you very briefly what research has been done on that subject, and that leads to defining my objectives. This is followed up by the methodology that I use throughout this study, and we end the simulation by results and conclusion. So our industrial partner is Hydro-Quebec, is the biggest electric producer of in entire Canada and top 5 in North America. And the energy production is mostly focused on the renewable energy. So more than 99% is produced that way. And this is mostly due to the hydropower plant. So where the energy from the water flow in the river will be converted to the electricity via turbine and the shaft connected to it. So the main domain of this project in this study is a Francis type turbine, which contains 3 main parts: blades, crown, and the bound. But what is the problem that we have with the industry? As you can see from the photo, comparing to the size of the human standing there, it's a huge component. So the only viable technique for manufacturing this is through casting the part of it, and then we need to connect them through welding. And when we do some fine element analysis, we see that the highest operating stresses are located at this connection where we have welding. And we all know that the welding and highest stresses result in fatigue problems, which leads to the crack initiation and propagation. But this problem is becoming more severe, knowing the fact that this turbine is located inside the case, and that case is located inside the dam well below the water level. So accessing the turbine is really difficult. So therefore, the repair that we can do is very limited. If we want to do a main repair, it will be very costly, and even the inspection is very difficult. So to just give you an idea, Hydro-Quebec do the interval inspection every 6 years. So we need to know that at least for 6 years, like running the turbine, it's working very well. For doing that, they have done some research, and I will show you briefly what they have done. So they did some study on the effect of microstructure aspect, like the different part of the material, like filler metal, heat affected zone, and base metal, and also they studied the effect of post-heat treatment and the residual stresses on the fatigue crack propagation. And then for the repair of the turbine, instead of like extracting the turbine out of the thing and do the heat treatment, they proposed to do some hammer pinning, which is introduced the compressive residual stresses. And they did that, and the results were very successful. So if they wanted to repeat the same process for the fabrication of the turbine at the beginning, due to the nature of the material and the microstructure, the result wasn't that successful. So they tried to enrich the material with nickel and manganese elements, which increase the stability of reformed austenite. They could change the microstructure, and hopefully we can have the benefit of hammer pin. So based on that, the objectives of my PhD project is defined in 2 ways. So first, I need to predict the fatigue crack growth rate using a computational models, considering that we have the impact from the compressive residual stresses to the hammer pinning. And then we need to evaluate the capability of the hammer pinning of 13.6, which is the new filler metal, as an alternative filler metal in our turbine. But due to the time limitation, I'm only going to present a specific part of this project, which will be predicting the cracked front shape under the influence of hammer pin. So starting from that, I'm going to show you the sample preparation. So this is the schematic of that. It included some steps, involves machining, depositing weld, and sometimes gouging. Also, I have a short video. I hope the sound is okay because it's very noisy. So you can see the noise. So this is the tool that we used for hammer pin. We did it on both surfaces. And when we got our plate, we machined our seating in such a way that the crack propagates only through the filament. And the fatigue tests were performed by Instrong test benchmark with the test sample size of the standard 1/2 an inch. Compliance method is used to measure the crack length. Also, it was verified optically by traveling microscope and the others. Residual stresses were measured, and we did that using the contour method. So basically, the idea behind that is if we assume that we have a sample that contains residual stresses, when we cut it in half, the residual stresses will be released and deform the cutting surfaces. If we measure the deformation and we implemented that in the finite element model, if we can estimate the residual stresses prior to the cutting. And here you can see the sample, the CT sample mounted on the bolt head, and this is the EDM cut. So the EDM cut cuts through the crack plane, the crack growth plane, and then I use a profilometer to capture that deformation. So the numerical simulation of this project, I used mainly this flow chart. So first we have the geometry loading and boundary condition, and then I inserted the parameter that I measured to explain the residual stress distribution and the fatigue propagation data. And then we insert a loop when we need to locally remesh the crack near the crack tip. And then we need to calculate the stress strengthening, and based on that, we can calculate the crack stress intensity factor. And finally, we can compute the fatigue crack growth rate along the crack line. And we repeat this procedure until all the steps are considered. This simulation mainly done by Abacus and Frank 3D simultaneously, and this is the type of element that I use for this simulation, and I guess is very typical in fatigue applications. So the specification of this model, so the geometry is the same as our experiment. So it's a CT specimen, and the stress ratio model. I had the data for 0.1 and 0.7, and I calculated the stress ratio along the surface, and based on using some interpolation and extrapolation technique, I calculated the crack growth rate for each point along the surface. The residual stresses were imported using a surface treatment model, and they were recording our contour method results, and you can see them. So on the sides, we have a huge antique layer of compressive on both sides, and it goes up to 400 megapascal. And then the loading sequences were selected somehow to replicate our experiment. So here you can see the fatigue crack growth model. So this is the animation. So at the beginning, the crack only propagates through the middle of the surface, but as it started to grow on the side as well, but the propagation rate is still much higher in the middle in comparison to the side. But as the cracks propagate and is forming a tunneling shape, this difference between the crack propagation rate on this side and through the middle decreases. So why this has happened? Besides that, I draw some graph here for like every 6 step. So as we started from there, we can say the stress ratio in the middle, the local stress ratio were much higher, and it's of course expected due to the tensile residual stresses that we had through the middle. And also we had the same behavior for the threshold. So the threshold is at the lowest when the tensile residual stresses are applied, and then the highest when you have the compressive residual stresses. Then we have the SIF due to the residual stresses. As you can see, the changes due to with the crack growth is not that much. So as the crack advances, the SIF increases, but the changes are trivial. So there are not that. But this wasn't the case for the SIF due to the loading. Uh, uh, as you remember, the loading sequence were decreasing, but the crack size is increasing. So these two phenomena balance each other out. So in the middle, the SIF stays kind of constant and similar, but as the crack forms and we have that tunneling shape, the driving force on the sides increasing, despite we have a decreasing load. So as you can see, like for example, the last one, the SIF on the sides is very huge. So for the experimental verification, we have the image of our sample after the cutting, and this is under the Keynes microscope. As you can see, the final crack front is very visible, and this is the result of simulation. And if we compare them, they almost follow the same trend. So to summarize my work, I would say that in this study, we were able to successfully develop a numerical procedure that was able to predict the crack front shape. Of course, there was some very, I would say, differences between the result of simulation and experiments, and that could be due to the scattered nature of the fatigue problem, and also some assumption that I made, like for example, I didn't consider the residual distribution and relaxation due to the fatigue growth. Also, we saw that the hammer pinning induced thick layer of compressive residual stresses, which retarded the crack growth on both sides. And also, I would say that this model is like a foundation for me to predict the fatigue crack growth rate in the real application, which is the Francis turbine, considering that we have a residual stresses from a hammer pin. And based on that, we can select the optimal fabrication technique and maintenance. And at the end, I'd like to thank you for your time.